The Mariana Trench has swallowed things that were never found again, and tonight we go looking for them. You are listening to Depth Unseen. Where light ends, the story begins. Tonight we go somewhere most humans will never go. Settle in, close your eyes, and drift with us. The Mariana Trench sits in the western Pacific Ocean, like a scar on the skin of the world. It is not just deep, it is the deepest, the most unreachable, the most misunderstood place on the entire surface of this planet. And here is the thing that most people do not know, the thing that should stop you cold the moment you hear it. We have sent humans to the moon more times than we have sent them to the bottom of the Mariana Trench, the moon, a place 250,000 miles away in the black silence of space. We have visited it more than we have visited a hole in our own ocean floor. Let that sit with you for a moment. Let it really sink in. There are places on this earth that resist us. Places that push back. Places that say, no, you are not ready. You are not built for this. You do not belong here. The Mariana Trench is one of those places. It has been here for 60 million years, carved into the floor of the Pacific as two enormous plates of the Earth's crust sky collided, and one slowly slipped beneath the other. Pacific plate dove downward, and the crust buckled and split and sank, and it kept sinking, and it kept sinking, till it formed the deepest wound the ocean has ever known. 60 million years of darkness, 60 million years of cold, 60 million years of silence, so profound that the word silence barely covers it, and we have barely touched it. We do not fully understand why. We tell ourselves it is the engineering challenges, the pressure, the cost, the technology. And all of those things are true. They are very real barriers. But there is something else, too. Something that scientists do not say in their papers. Something that explorers only whisper about after a few drinks in a harbour bar somewhere. There is a feeling, when you begin to understand what the Mariana Trench truly is, that you are not supposed to go there. Not yet. Maybe not ever. The ocean has kept it dark for a reason. And the reason is not one we are meant to understand from the surface. Tonight, we are going to try. Anyway, we are going to go down, all the way down. We are going to look at every reason why humanity cannot truly explore the Mariana Trench. And we are going to understand why those reasons feel less like physics and more like a warning. But first, let us make sure you know where we are going. Picture the Pacific Ocean. It is the largest body of water on Earth. It covers more ground than every single continent combined. If you took all the land on the planet, every mountain, every desert, every city, forest, and piled it into the Pacific, the ocean would still have room left over. That is how large this ocean is. Deep within its western edge, near a chain of small volcanic islands called the Mariana Islands, there is a place where the ocean floor simply gives way. It drops, and it does not stop dropping for a very, very long time. The Mariana Trench stretches roughly as 550 kilometers long and about 69 kilometers wide. Think of it as a crescent-shaped gash in the planet, longer than the entire country of India from north to south. And at its deepest point, a place called Challenger Deep, the ocean floor sits nearly 11,000 meters below the surface. That is about 11 kilometers, about 6.8 miles, straight down. Now, 11 kilometers might not sound like much if you are thinking in road terms. You could drive 11 kilometers in about 8 minutes. you could walk it in 2 hours. But when those 11 kilometers are straight down, when above you is not road or sky, but an entire ocean pressing down with all its weight, the distance becomes something different. Distance becomes something living, something with teeth. Here is a way to feel it. Mount Everest, tallest mountain on the surface of the Earth, stands about 8.8 kilometers tall per ot. If you picked up Mount Everest and dropped it into the Mariana Trench, the very tip of it, the summit that climbers struggle and suffer and sometimes die to reach, would still be more than 2 kilometers underwater, more than 2 kilometers below the surface. The entire mountain would disappear, and there would still be ocean above it. That is where we are going tonight. And here is what is waiting for us there. Nothing. Or at least, that is what scientists believed for most of human history. The deep ocean, the very deep ocean, was thought to be a dead zone, a place where nothing could live. And honestly, the reasoning made sense at the time. Life as we understand it needs certain things. Warmth, light, nutrients, somewhere to stand. The deep ocean offers none of those things. The temperature at the bottom of the Mariana Trench hovers just a few degrees above freezing. Not zero, because the incredible pressure keeps the water from turning to ice. But cold enough that your body would stop working very quickly. There is no light. Not a single photon of sunlight has ever reached the floor of the Challenger Deep. Creature down there has lived its entire life in a darkness so complete. That we do not have a word in the English language that quite describes. And the pressure. The pressure is the thing that haunts every engineer, every diver, every submarine designer who has ever turned their attention toward the deep. At sea level, the atmosphere presses down on you with 1 unit of pressure. That is what your body is built for. That is the pressure your bones and organs and blood vessels expect. For every 10 meters you descend into the ocean, pressure increases by 1 more unit. So at 10 meters deep, you feel 2 units of pressure. At 100 meters, 11. 1,000 meters over 100. At the bottom of the Mariana Trench, you are feeling over 1,000 units of pressure, 1,000 atmospheres pressing down on every single square inch of your body. Scientists have compared it to having 50 full-sized passenger jet airplanes stacked on top of you. Every square inch. Not just your shoulders, every square inch of your skin, your skull, your chest, your eyes, pressing in from every direction at once. A human body exposed to that pressure, without protection, would not simply be crushed. It would not have time to be crushed in the way you might imagine, with bones breaking and flesh tearing. It would simply compress. Fluids and gases inside you would behave according to the laws of physics, and those laws would reduce you to something much smaller than you currently are, very quickly, in a way that is almost peaceful in its efficiency. The ocean does not hate you. It simply does not know you are there, and yet, life is there. When Jacques Piccard and Don Walsh descended to the Challenger Deep on January 23rd, 1960, in a vessel called the Trieste, they expected darkness and emptiness. What they found, or what Piccard believed he saw through the small, thick porthole of their submersible before silt clouded the view, was a flatfish. A fish, living, moving, breathing. If fish breathe is the right way to put it, at the bottom of the world. Piccard was so shocked that some scientist later questioned whether what he saw was real. whether it might have been a sea cucumber or a trick of tired eyes after a 5-hour descent into the dark. But the question had been asked, and it could not be unasked. Is there life at the very bottom of the world? And if there is, what is it? How does it survive? What does it look like? Having never once seen light, what does it eat? What does it dream about? If dreaming is even a thing that happens in that cold and crushing dark, we still do not fully know. And that is the beginning of the reason why we cannot truly explore the Mariana Trench. Not the engineering, not the cost. Beginning of the reason is simpler and stranger than both of those things. We do not know what we are looking for. We have no map. We have no catalogue. We have no understanding of what a complete ecosystem at the bottom of the earth even looks like. Which means we do not know what tools to bring, what questions to ask, what data to collect. Single expedition to the deep has returned with surprises. Creatures nobody expected. Chemistry nobody predicted. Sounds nobody could explain. Host. The Mariana Trench is not just unexplored. It is unexplored in a way that keeps redefining what unexplored means. Let us talk about what we do know, because what we know is astonishing enough. The trench was first discovered, or rather, first measured in a serious way, by the British survey ship HMS Challenger in 1875. The Challenger was not a military vessel and not a luxury ship. It was a converted warship that had been stripped of most of its guns and filled with scientific equipment instead, sent out into the world by the Royal Society of London to simply see what was there. Crew of the Challenger spent nearly 3.5 years at sea, sailing more than 127,000 kilometres, dropping weighted ropes over the side to measure depth, dragging nets through the water to catch whatever lived there, recording temperatures and pressures and currents, with instruments that now look almost childishly simple. When they dropped their weighted rope over the side near the Mariana Islands, and it kept going, finally stopped at a depth that none of them could quite believe. They recorded it in their logs and moved on. They did not know what they had found. They had no way of truly understanding it. They just wrote down the number, 8,184 metres, and continued their survey. Trench that would eventually be measured at nearly 11,000 metres was noted as unusually deep, and that was essentially all. We named the deepest point of the trench after them anyway. Challenger Deep, a name that carries both the weight of that first accidental discovery and the impossibility of the thing they found. But here is something that should make you feel a particular kind of small, a particular kind of humbled. That was almost 150 years ago. And we have still barely gone back in all the time between that first measurement in 1875 and the day you are lying here listening to these words. We have sent humans to the very bottom of the Mariana Trench exactly a handful of times. A handful. You could count them on one hand. First manned descent in 1960. James Cameron's historic solo dive in 2012. A small number of additional dives by the submersible limiting factor in the years since, the most recent. Adding a few more names to the tiny, exclusive list of humans who have touched the deepest floor. More than 300 people have reached the summit of Mount Everest in a single year. the Mariana Trench has received fewer human visitors in its entire recorded history of exploration. Why? The honest answer is that we are not built for it. Nothing about the human body is designed to go there. We are, in the most literal possible sense, creatures of the surface. We evolved under open sky, breathing a mixture of nitrogen and oxygen at 1 unit of pressure, sunlight warming our skin, and gravity pulling us reassuringly downward. Take any of those things away, and the human body begins to protest immediately. Take all of them away at once, as the deep ocean demands, and the human body becomes a very delicate, very expensive, very worrying liability. Consider what happens to a submarine, which is a machine built specifically to withstand underwater pressure, as it descends toward the Mariana Trench. The hull, no matter how thick, no matter how carefully engineered, must deal with the fact that pressure at those depths is not simply pushing inward from one direction. It is pushing inward from every direction simultaneously with a force so uniform and relentless that any weakness in the structure, any microscopic flaw in the metal or the welding or the seals around the portholes will be found and exploited almost instantly. Forced. The ocean at that depth is not searching for weaknesses the way a curious person searches. It is applying pressure the way gravity applies pressure. Everywhere, always, everywhere, without pause. The submersible that James Cameron used for his 2012 dive, the Deep Sea Challenger, was a remarkable machine. It was a vertical torpedo shape, about 7 meters tall, designed to sink and rise straight up and down rather than moving horizontally through the water. It was built with a pressure sphere, tiny space where Cameron actually sat, made of specially engineered steel, about 64 millimeters thick, designed to protect the single human body inside it from over 16,000 pounds per square inch of force. Cameron spent 7 hours descending. He spent 3 hours at the bottom. The sphere held. He came back, but while he was down there, the manipulator arms on the outside of the submersible, the metal arms designed to collect samples and interact with the environment, failed. Thrusters had problems. The three-dimensional camera system that he had planned to use to film the environment in unprecedented detail was not working as expected. He had designed this machine for years. He had tested it extensively. He had some of the best engineers in the world working with him. And still, in the environment of the deep trench, things broke. Things that should not have broken, broke. Because the Mariana Trench does not care about engineering timelines and testing protocols. It does not care about your plans. The temperature fluctuations, the pressure, the simple passage of time in that environment caused materials to behave in ways that had not been fully predicted. And Cameron, alone in a steel sphere at the bottom of the world, with systems failing around him, made the decision to come back up. He had data, he had samples, he had seen things. But he had not seen everything he came to see. He came back and described the bottom of the Challenger Deep as a vast, flat, desolate plain. Lunar. He used the word lunar. The floor of the deepest place on Earth reminded him of the surface of the moon. Flat, grey, of everything obvious. Just sediment stretching away in every direction into a darkness that his lights could not reach far enough to end. But the sediment is not empty. That is the thing. That grey flat plain that looks like nothing is full of life, so small, so specialised, so perfectly adapted to those conditions, that our instruments struggle to detect it and our minds struggle to accept it. In the sediment of the Challenger Deep, scientists have found microorganisms called foraminifera, single-celled creatures so tiny that you would need a microscope to see them, living inside tiny shells of their own making, going about their lives at the bottom of the world, as if the crushing pressure, the total darkness and the near-freezing temperature are perfectly normal conditions, because for them they are. These are not organisms that have been pushed to the edge of survival. These are organisms that evolved specifically for this place. The trench is not their prison, it is their home. And that realization, that simple biological fact, is one of the things that makes the Mariana Trench so deeply strange and so deeply compelling. We assumed that the deep was empty because we assumed life needed what we need. And life, it turns out, far more creative and far more stubborn than we gave it credit for. But here is the thing that keeps scientists awake at night. Foraminifera can live there. If amphipods, tiny shrimp-like creatures, can live there in enormous numbers, crawling through the sediment and scavenging whatever falls from the world above. If snailfish, pale and translucent, can live at depths below 8,000 meters, which is deeper than almost anyone imagined, a vertebrate, a creature with a spine could survive. All of these creatures are there, living and feeding and reproducing in the dark. Then what else is there? What has the trench kept hidden that we have not yet found? We have explored less than 5% of the world's oceans. Less than 5%. Proud. The ocean covers more than 70% of the Earth's surface, and we have meaningfully examined less than a 20th of it. We have better maps of the surface of Mars than we do of our own ocean floor. Read that sentence again. Mars, the red planet, 140 million miles away at its closest approach. We have mapped its surface in more detail than we have mapped the floor of the ocean we swim in. The ocean that regulates our climate and produces more than half of the oxygen we breathe. The Mariana Trench is the most extreme version of this ignorance. It is the farthest point from everything we know, the darkest corner of the most unexplored habitat on our planet. And every time we send something down there, we come back with questions we did not think to ask before we left. There is a species of snailfish, the Mariana snailfish, the deepest living fish ever recorded, that was filmed at more than 8,000 meters. Meters depth by a research team in 2017. It is a pale, ghostly creature, almost translucent, with small, dark eyes that appear almost vestigial, almost as though the fish knows that eyes are not useful here, and is slowly, over generations, forgetting about them. Feeds on tiny crustaceans that fall into the trench, and it moves with a kind of slow, dreamy grace that seems almost impossible given the pressure it is navigating. Its body contains high concentrations of a compound called trimethylamine oxide, which essentially works as a kind of internal pressure management system, preventing the molecules in its cells from being deformed and destroyed by the crushing force around it. Its bones are flexible rather than rigid. Its skull is not a solid dome the way yours is. It is more like a loose cage of cartilage that can absorb pressure rather than resist it. it has solved the problem we cannot solve. It has found a way to be in that place, and it does not find that place hostile at all. It is simply where it lives. And there may be things far larger that we have never seen. The deep ocean has a history of hiding giants. The giant squid, Architeuthis dux, was considered a myth for most of human history. Sailors told stories of monsters as big as ships, creatures with arms like ropes that could drag a vessel underwater. Scientists dismissed these stories as the exaggerations of frightened men who had been too long at sea, and then we found one, and then we found more, and now we know that the giant squid is real, that it grows to lengths of around 14 meters, and that its primary predator is the sperm whale, which dives to enormous depths to hunt it, and which surfaces sometimes with circular scars on its skin from the squid's suckers that are large enough to put your head through. The giant squid was not photographed alive in its natural habitat until 2004. 2004. Creature, the size of a school bus living in the ocean, was not seen alive on film by human beings until 22 years ago, because the ocean is very good at keeping its secrets. So, when people ask whether there are large unknown creatures in the Mariana Trench, the honest scientific answer is not no. The honest scientific answer is that we have not looked enough to know that the deep ocean has surprised us before, and that the physics of the deep trench, the pressure, the darkness, the cold, would in some ways favour very large, so slow-moving creatures with efficient metabolisms. There is food in the trench. Things fall from the world above, constantly, in a gentle rain of organic material that scientists call marine snow. Particles of dead organisms, fecal matter, mucus, all of it drifting down through the water column, slowing as it goes, carrying nutrients from the sunlit upper ocean to the eternal dark below, Haddle Zone. That is the name for ocean depths below 6,000 meters, from the Greek word Hades, the underworld. Scientists gave it a name that means the realm of the dead, and that tells you something about what they expected to find there. But what they have found, even in the limited explorations that have happened, is not death. It is life operating on completely different terms, life that has abandoned every assumption we brought with us from the surface, Proust, life that has turned the most hostile conditions on the planet into a home. The walls of the trench are not empty either. They are studded with xenophyophores, single-celled organisms that grow to sizes of up to 20 centimeters, making them the largest single-celled organisms on Earth. A single cell, no brain, no nervous system, no organs, just one cell going about its life, growing to the size of a softball at the bottom of the Mariana Trench. If that does not make you question everything you think you know about what life is and what life can do, then perhaps nothing will. But we are getting ahead of ourselves, because before we can talk about what is in the trench, we need to really understand why we cannot get to it properly. Not just the broad strokes, real reasons. The granular engineering and scientific reasons that have kept humanity from truly mapping and understanding a place that sits on our own planet. And those reasons are more humbling than you might expect. The pressure we have talked about, but there is another element of the deep that gets far less attention, and it is, in some ways, even more limiting than the pressure. 'Tis the darkness. Not darkness the way a room is dark when you turn off the lights. Not darkness the way a cave is dark, where your eyes eventually adjust and find faint shapes. This is absolute darkness. Photons of sunlight penetrate the ocean to a maximum depth of about 1,000 meters. And that is in the very clearest, most sunlit tropical water. Below 1,000 meters, there is no sunlight. None. Below 1,000 meters, creature that wants to see must either make its own light or learn to live without seeing. By the time you reach the bottom of the Mariana Trench, you are 10 times deeper than the last photon of sunlight. 10 times. The darkness there is older than most species on Earth, and it is a darkness that has existed unchanged for millions of years. And into that darkness, we must send cameras. We must send lights. We must try to illuminate with our little human-made bulbs space so vast and so dark that our light dies within meters of its source. When Cameron descended in the Deep-Sea Challenger, his lights could illuminate only a small circle around the vessel. The trench stretched away in every direction into a dark that his cameras could not reach. He could see the floor immediately beneath him. He could see a small radius of that grey, flat plain. But the trench is 69 kilometers wide at its widest, and his circle of light covered perhaps 10 meters in any direction. He was a single candle in a room the size of a country, and he was there for 3 hours. 3 hours. In 60 million years of history, put in a space 69 kilometers wide and nearly 11 kilometers deep, we have had 3 hours of imperfect, cloud of silt limited human observation. And we call that an exploration. There is something almost heartbreaking about that, something that speaks to the size of the universe and the smallness of everything we have ever done within it. But we are trying. We keep trying. The story of those attempts, and why they keep falling short, is the story we are telling tonight. Because every attempt teaches us something new, not just about the trench, about ourselves, about the limits of our tools and our bodies and our imagination, about what it means to want to understand something so completely foreign to our nature that even the attempt to approach it is a kind of miracle. First thing you need to know about exploring the Mariana Trench is that the trench does not want to be reached. Not in a conscious way. Not in the way that a living thing might resist an intruder, but in the way that the laws of physics themselves seem to conspire against entry. Consider the journey down. It takes roughly 5 to 7 hours to descend to the Challenger deep in a vessel, moving at a controlled rate. 5 to 7 hours of darkness. 5 to 7 hours of increasing pressure. 5 to 7 hours of cold seeping into the metal of the hull contracting slightly as the pressure builds, of every seal and weld and joint in the vessel being tested by forces that increase continuously and stop increasing only when you reach the bottom. During those 5 to 7 hours, you are also losing contact with the surface. Radio waves do not travel through seawater. Not far, anyway. The submersible communicates with the support ship above via acoustic signals, essentially sound waves sent through the water. But this communication is slow and limited. You cannot stream video from the bottom of the Mariana Trench. You cannot send a real-time signal. You cannot, if something goes wrong, call for help in any meaningful way. The support ship above cannot reach you. There is no rescue vehicle for the Challenger Deep. If something goes wrong at 11,000 meters, the people on the ship above can drop a transponder and wait and hope. That is all. Cameron knew this. Pickard and Walsh knew this. Every person who has made that descent has understood, truly understood, that they are completely alone in a way that very few humans in history have ever been alone. Not alone in an empty room. Alone at the bottom of the deepest wound in the world. With an entire ocean above them, with no possibility of help from any direction, with a machine that could fail in a dozen ways, each of them final. That knowledge changes how you think. It changes what silence means. It changes what darkness means. You are not exploring, you are visiting. Briefly, on terms set entirely by the Trench. This is why we cannot truly explore the Mariana Trench. Not yet, not really, because exploration requires time. It requires the ability to stop and then look again. To return to the same spot in different conditions, to set up instruments and leave them and come back for the data. Real exploration requires presence, and the Mariana Trench makes presence almost impossibly expensive and dangerous. There have been unmanned vehicles, remotely operated vehicles, or ROVs, tethered to a surface ship by cables that carry power down and data up. These machines can go deeper than humans. They do not need air. They do not need pressure spheres for living bodies. They can be built smaller and stronger, and they can stay down longer without the life support concerns that limit manned dives. The ROV Nereus reached the challenge deep in 2009. It spent about 10 hours at the bottom, collecting samples, taking photographs, mapping small sections of the floor. It sent back images that scientists studied for years. And then, 2014, on a subsequent dive, in a different location, Nereus imploded. The pressure found a flaw, or created one, and the vehicle simply ceased to exist as a functional machine. Pieces of it floated to the surface. The rest stayed down, in the pressure of the deep ocean. A mechanical failure does not mean a broken machine. It can mean instant destruction. Human crew inside a vessel that suffers a catastrophic implosion at those depths would not survive. They would not suffer. They would simply be gone. This is the reality of the Mariana Trench. It does not offer second chances. And yet we go, and we will keep going, because there is something in the human relationship with the unknown that cannot be satisfied by maps and theories and data collected from far away. We need to go. We need to see. We need to stand in whatever sense standing is possible at 11,000 meters beneath the sea and look around and try to understand with our own senses what this place is. That need, that stubborn, slightly irrational, deeply human need to go to the places that resist us. It is why this exploration keeps happening despite the costs and the failures and the losses. Tonight, as you lie here and let the story of the deep wash over you, you are, in your own way, part of that need. You are reaching, with your imagination, toward a place your body cannot go. And in that reaching, you are doing something that is uniquely human. We have only just begun. The trench is 11 kilometers deep, and we have only descended in this the first few hundred meters. There are currents below us that behave in ways that still surprise scientists. Roused. There are geological processes taking place at the very bottom that connect directly to the movement of the planet's tectonic plates, the same forces that cause earthquakes and build mountains. There are chemical reactions. There are chemical reactions much on inhabiting in the sediment that have implications for the carbon cycle, for the climate, for the chemistry of the ocean as a whole. And there is still the question, the quiet, persistent, never quite answered question of what is alive down there that we have not yet found. What has been found already should make your breath slow and your mind go very still, because the answer is stranger and older than anything science expected to find. The Mariana Trench does not give up its secrets easily. What science has pulled from its darkness in the last 2 decades has rewritten everything we thought we understood about life on this planet. We left you at the edge of something. A question left open like a wound. What has been found down there that science did not expect? And the answer, when you hear it fully, when you let it settle into your understanding, the way sediment settles to the bottom of the deep, change the way you think about life itself. Not just ocean life, all life, including yours. But first, we need to go back. We need to go back to the science of the trench itself, the physical reality of what it is and what it does, because until you understand the trench as a place, as a living geological system rather than simply a very deep hole, cannot truly understand why exploring it is so much harder than any other challenge humanity has ever attempted. Mariana Trench exists because of a process called subduction. That word, subduction, comes from the Latin for to lead away from below, and that is almost exactly what is happening. The Pacific Plate, an enormous slab of the Earth's outer shell, is being led away from below. It is diving, slowly, relentlessly, downward into the interior of the Earth, beneath the smaller Mariana Plate, at a rate of roughly a few centimeters per year. A few centimeters. That sounds like nothing, but multiply a few centimeters by 10 million years, and you begin to understand the scale of what is happening. Pacific Plate has been subducting beneath the Mariana Plate for approximately 60 million years. In that time, the diving edge of the Pacific Plate has pulled the ocean floor above it downward, creating the trench the way a tablecloth bunches and sags at the edge of a table. When you pull one end downward, the ocean floor has been sagging into that descent for 60 million years. And the result is the deepest place on Earth. And it is still happening, right now. As you breathe, as your chest rises and falls in the quiet of wherever you are lying, the Pacific Plate is moving. The trench is deepening, perceptibly, by fractions of a fraction of a millimeter. On human timescales, it seems perfectly still. On geological timescales, it is in constant violent motion. This movement is not just interesting geology. It is one of the reasons the Mariana Trench is so difficult to explore. The subduction zone is seismically active. The collision of plates generates earthquakes, and the Mariana region experiences seismic activity regularly. An underwater earthquake near a submersible at the bottom of the trench would not be a gentle tremor felt as a slight vibration. At those depths, seismic event can generate pressure waves through the water, powerful enough to affect equipment and communication. Scientists planning deep dives must monitor seismic activity constantly. They must be prepared to abort at any moment. The Earth itself is one more variable in an already impossibly complex equation. There is something both beautiful and terrifying about that. Trench is not passive. The trench is being created by the movement of the planet, And the planet does not pause for scientific expeditions, but let us go deeper into what the trench actually contains. Not the floor which we will return to, but the water column itself. The long, dark, cold descent from the surface to the bottom. Because this water column is not empty space. It is not simply the gap between here and there. It is a world unto itself, a series of worlds stacked one on top of another, each one darker and colder and more pressurized than the one above. Each one home to organisms that have evolved specifically for that precise depth, that precise pressure, that precise temperature. Host. The ocean is divided into zones based on depth. The sunlit zone, from the surface down to about 200 meters, is where almost all of the ocean's photosynthesis happens. This is where the phytoplankton live, the microscopic plant-like organisms that produce more than half of the oxygen in every breath you take. Above you right now, in the surface layers of the Pacific Ocean, near the Mariana Islands, phytoplankton are converting sunlight into oxygen and organic carbon. That carbon, when the phytoplankton die, begins a long, slow journey downward. Below the sunlit zone is the twilight zone, from 200 meters to 1,000 meters depth. This is a world of half-light and strange shadows, where the last fragments of sunlight filter down as a dim blue-green glow that fades as you descend, until around 1,000 meters is gone entirely. The twilight zone is full of creatures that perform one of the most remarkable migrations on Earth. Every single night, millions upon millions of fish, squid, shrimp, and other organisms rise from the twilight zone toward the surface to feed on the phytoplankton there. Every single morning, as light begins to return, they descend back into the darkness. The largest migration on Earth, happening every day, in the dark, beneath every ocean, almost completely invisible to us. Below 1,000 meters, the midnight zone, no sunlight ever, temperature dropping to just a few degrees above freezing. Pressure increasing with every meter. Creatures here have adapted in ways that defy easy description. The anglerfish, which you may have seen in illustrations, real and it lives here. The female grows a bioluminescent lure from her forehead, a light-producing growth that dangles in front of her jaws in the absolute darkness, attracting prey that mistakes the glow for something edible. Produced. The anglerfish produces her own light using symbiotic bacteria that live in the lure and create bioluminescence, which is light produced by a living creature without heat, purely through chemical reaction. She cannot see far. She does not need to. She sits, nearly motionless in the dark, and lets the light do the work. Bioluminescence. This word deserves a pause because it is one of the most extraordinary phenomena in the natural world, and it is almost entirely hidden from us because it happens in the dark of the deep ocean. Scientists estimate that approximately 76% of deep-sea creatures produce their own light. 76%. 3/4 of all animals in the deep ocean glow. They glow to attract prey. They glow to communicate. They glow to confuse predators. They glow to find mates in the absolute absence of all other light. Some produce flashes. Some produce a constant soft luminescence. Some can control the colour and intensity of their light. And we barely know any of them. Midnight zone gives way, below 3,000 meters, to the abyssal zone. From the Greek abyss, meaning bottomless, here the ocean floor begins in earnest. a vast flat plain called the Abyssal Plain that stretches for thousands of kilometers at depths of between 3,000 and 6,000 meters. The Abyssal Plain covers more than half of the Earth's surface. It is the most common environment on the planet, more common than forests, more common than grasslands, more common than deserts, and we know almost nothing about it. Marine snow falls here. That term again. Marine snow. It sounds delicate, it sounds almost beautiful, and in a way it is. From the sunlit surface, a constant gentle rain of organic particles drifts downward, dead organisms, fragments of things that were once alive and are now making their last journey. Fecal pellets, which are the waste products of ocean creatures, wrapped in mucus and dense enough to sink. Mucus webs produced by filter feeders, enormous transparent structures, sometimes the size of a house, that collect particles from the water and then sink when they become too heavy. All of this falling, slowly, through thousands of meters of dark water, being eaten and re-eaten by creatures. At every depth, each layer extracting a little more nutrition, till what finally reaches the abyssal plain is a sparse, thin dusting of organic matter. And yet, from that sparse, thin dusting, an entire ecosystem has arisen. Sea cucumbers crawl across the abyssal plain in enormous numbers, hoovering up sediment and extracting nutrition from what is essentially the ocean's exhaust. Brittle stars spread their long, delicate arms across the mud and filter, feed on whatever passes by. Polycheatworms, bristly segmented creatures that look something from a science fiction illustration, burrow through the sediment, processing organic material that would seem to any surface creature impossibly nutritionally poor. Life has found a way. Life has always found a way. But below the abyssal plain at depths greater than 6,000 meters is the Huddle Zone, the Trench Zone, the underworld. And in the Huddle Zone, something remarkable happens that scientists are only beginning to understand. The trenches are not just deep extensions of the abyssal plain. They are different in character, different in chemistry, different in the nature and density of the life they support. The narrow walls of the trench funnel the marine snow that falls across a wide area of abyssal plain into the confined space of the trench itself. The trench acts like a trap. Organic material that falls near the trench gets caught in the slow currents of the Huddle Zone and concentrated at the bottom floor of the Mariana Trench may receive more organic material per unit area than the surrounding Aldley abyssal plain. It may actually be, in certain ways, a richer feeding ground than the waters immediately above it. This was not predicted. This was not expected. Scientists assumed that the deepest parts of the ocean would be the most food poor, the most barren, and instead they found that the geometry of the trench creates a kind of funnel system that enriches the bottom. Life was not supposed to be abundant in the Huddle Zone, and yet in some forms, in the tiny amphipods that swarm in enormous numbers through the sediment, it is. And here is where things become genuinely strange. The amphipods of the Mariana Trench, tiny crustaceans related to the sandhoppers you might find on a beach, have been studied in some detail because they are relatively easy to capture, with baited traps lowered to the trench floor. Drop a weighted cage with some fish bait attached. Wait a few hours, pull it up, and the traps come back full of amphipods, thousands of them sometimes. swarming over the bait in the darkness with an energy and enthusiasm that seems somehow completely at odds with the oppressive hostility of their environment. They are not struggling, they are thriving. When scientists analyze the bodies of these amphipods, they found something that stopped them cold. Inside the bodies of creatures living at the very bottom of the Mariana Trench, they found polychlorinated biphenyls, PCBs, persistent organic pollutants, manufactured chemicals that were produced industrially between the 1920s and the 1970s, used in electrical equipment and industrial processes banned in most countries in the 1980s because of their extreme toxicity. PCBs do not naturally occur in the environment. Every molecule of them was made by human industry. And they were found in creatures living at the bottom of the deepest place on Earth. A place where no human being has ever stood, a place that feels as remote from human civilization as it is possible to get on this planet. A concentration of PCBs in the Mariana Trench amphipods was comparable to or higher than the concentration found in organisms living in the most heavily polluted rivers and bays in the industrialized world. The Suruga Bay in Japan, the Pearl River estuary in China, places directly adjacent to industrial activity. The Mariana Trench, 11 kilometers below the surface of the Pacific, far from any industry, in the deepest, most isolated corner of the ocean, was as contaminated as these heavily polluted coastal environments. Let that sit with you. The full weight of what that means descend upon you the way pressure descends as you go deeper. There is nowhere left on Earth that is beyond our reach. Not the summit of the highest mountain, not the interior of the thickest forest, not the most remote Pacific island, and not, it turns out, the bottom of the deepest trench in the ocean. Humanity has contaminated the Mariana Trench without ever truly visiting it. Our pollution travels the same paths as the marine snow, grouse, host. It enters the ocean at the surface in the form of an industrial runoff and the breakdown of plastic and the settling of atmospheric contamination, and then it does what everything else in the ocean does. It sinks, it drifts, it enters food chains. It gets concentrated as predators eat prey and absorb the pollutants their prey contained, and those pollutants pass from organism to organism down through the water column, becoming more concentrated at each step until they reach the bottom. The Haddle Zone, scientists now believe, may be a fixung for persistent organic pollutants, a place where they accumulate in the sediment and in the bodies of organisms, and remain in the cold and dark and pressure for decades or centuries, unable to be broken down. The trench that we have barely visited is storing the record of our industrial history in the bodies of creatures that live beyond our reach. This discovery, published in 2017 in the journal Nature, Ecology and Evolution, did not receive the widespread attention it deserved. But among ocean scientists, it sent a shockwave through the community, because it meant that the most extreme, most isolated environment on the planet was not isolated at all. It was connected to the surface world in ways that we had not appreciated. Those connections were carrying our worst mistakes into the deepest dark, and that is not all that has been found in the trench that should not be there. Microplastics, tiny fragments of plastic that result from the breakdown of larger plastic items in the ocean. Pieces so small they are measured in micrometers, found in the sediment of the Challenger Deep. They have been found in the bodies of amphipods there. They have been found in the water of the Hadal Zone. Plastic, which has existed as a material for less than a century, has already reached the bottom of the deepest place on Earth. The trench that took 60 million years to form has, in less than 100 years, received our plastic. The implications of this for the ecosystems of the Hadal Zone are not yet understood. That is honest science. We do not know what microplastics do to organisms in the deep trench use, because we have not had enough time to study it, and we do not have enough access to the trench to observe the effects. But we know they are there, and we know that microplastics in the surface ocean and in coastal environments measurable effects on the organisms that can consume them, disrupting hormone systems, blocking digestive tracts, carrying additional toxic compounds absorbed from the surrounding water. The trench is not pristine. Trench is not a preserved relic of a pre-human world. It carries our fingerprints. That knowledge changes the nature of what exploration there might mean. We are not going to discover a virgin environment. We are going to discover an environment that we have already touched, already altered without meaning to, without even knowing we were doing it. And in the middle of that melancholy realization, there is still wonder. There is still astonishment, because the organisms that live in the Hadal Zone have adapted to the trench conditions over millions of years. A host, and those adaptations are so extraordinary, so biologically creative, that they offer scientists windows into possibilities that have implications far beyond the deep ocean. The snailfish. We mentioned it before, that ghostly translucent creature found at depths below 8,000 meters. Its full name is Pseudoliparis swinhoae, and it holds the record for the deepest fish ever recorded by video camera, filmed at 8,336 meters depth in the Mariana Trench in 2022, shattering the previous record. It is a fish that should not exist. By all of the principles that governed marine biology for most of the 20th century, no vertebrate with a spine and internal organs should be functional at those pressures. And yet, it is not merely functional. It is, by the standards of the trench, successful. The snailfish appears to be a dominant predator in the Hadal Zone, eating the amphipods and other small invertebrates in significant numbers. It has solved the pressure problem through a combination of adaptations that took millions of years of evolution to arrive at, and that scientists are still working to fully understand. The trimethylamine oxide we mentioned in part 1, that pressure stabilizing compound, host, its concentration in the snailfish is higher than in any other fish species ever analysed. This compound works at a molecular level, protecting the proteins and enzymes in the fish's cells from being deformed by pressure. Proteins are the machines of biology. They do everything in a living cell, nor feeding oxygen from transporting oxygen to catalysing chemical reactions to building structures, host, and they work because their shape is precisely right for their function. Change the shape, and you break the machine. Pressure changes the shape of proteins. High enough pressure, and the proteins of a normal fish would unfold and stop working, and the fish would die. The snailfish has so much trimethylamine oxide in its cells that the pressure at 11,000 meters, pressure that would kill virtually any other vertebrate instantly, and simply cannot get enough grip on the proteins to deform them meaningfully. Fish is chemically armoured against the one thing that makes the trench uninhabitable for everything else we know. Its bones are also different, not just flexible, but actually reduced. The skeleton of the snailfish is cartilaginous and gelatinous in a way that means the fish is, in a sense, mostly water. A human body is about 60% water. The deep-sea snailfish is closer to 90%. This high content means there is very little rigid structure to be compressed and damaged by pressure. You cannot crush water. Water is effectively incompressible. So a body that is mostly water, with very little air or rigid structure, experiences the pressure of the deep differently than a body built for the surface. Think about that. The fish has evolved to become, in essence, much like the water it lives in as possible. It has minimized the difference between itself and its environment. It does not resist the trench, resembles it. That is a solution to the problem of the deep so elegant that it almost sounds like something that was designed rather than evolved. And that elegance is everywhere in the Huddle zone. If you look closely enough, every organism, there is a testament to the creative power of evolution over millions of years, an experiment in how far life can bend its rules before the rules break entirely. And the rules down there bend very far indeed. There is a type of bacteria that lives in the sediment of the Mariana Trench that can survive and appear to thrive pressures far above even what the trench floor provides. In laboratory experiments, these bacteria, called piezophiles, meaning pressure lovers, cultured at simulated trench pressures and show no signs of distress. Some grow better at high pressure than at normal pressure. They are not merely adapted to the trench. The trench is where they perform best. They are optimized for an environment so hostile to us that we cannot survive there, unprotected for even a moment. These bacteria are not just biologically interesting. They may be medically useful. The enzymes they produce to function at extreme pressure behave differently from normal enzymes in ways that have applications in biotechnology and medicine. Scientists have isolated compounds from deep-sea piezophiles that have shown potential in cancer research. Chemistry of organisms that evolved at the bottom of the world is a library of biochemical innovations that life at the surface never needed to develop. We have barely opened the first page of that library. And here is the thing that sits at the centre of everything we have been building toward tonight. The thing that the Mariana Trench, in its vastness and darkness and inaccessibility, is trying to tell us. Life is not fragile. We tend to think of life as fragile because the life we know best, our own lives and the lives of the organisms we can see and touch and study easily, requires fairly specific conditions. The right temperature, the right pressure, the right chemistry. Take any of those things away, and things begin to die. And so we assume that life in general is fragile, that it requires care and the right conditions to persist. The Mariana Trench is a direct contradiction of that assumption. The Mariana Trench says, no, life is not fragile. Life is relentless. Life is creative beyond your ability to anticipate. Life will find a way into the most pressurized, coldest, darkest, most chemically extreme place on the planet, and it will not merely endure there. It will build ecosystems. It will develop hierarchies of predator and prey. It will evolve tools, chemical and physical and behavioural, to exploit every possible resource. It will turn the very conditions that exclude all familiar life into the conditions it specifically requires. This has enormous implications that extend far beyond the ocean. One of the great questions of science, one of the questions that has animated astronomers and biologists and philosophers for centuries, is whether life exists elsewhere in the universe. Most of human history, the thinking on this question has been constrained by what we know about life on the surface of the Earth. We assumed that life needed sunlight. We assumed it needed liquid water within a narrow temperature range. Assumed it needed atmospheric pressures similar to what we experience on the surface. And we looked at the universe through that lens, identifying planets and moons that matched those surface Earth conditions as potentially habitable. The deep ocean changed that thinking. The discovery of life around hydrothermal vents, hot springs on the ocean floor where scalding, chemically rich water pours out of cracks in the Earth's crust, showed us that life could exist without sunlight entirely, powered entirely by chemical energy from the Earth's interior. The discovery of organisms in the Hull zone showed us that life could function at pressures and temperatures that we had assumed were definitively lethal. And once those discoveries were made, once the goalposts of what life needs moved, everything changed. Scientists began to look at places in our solar system that had previously seemed promising. Europa, one of Jupiter's moons, covered in a thick shell of ice with a deep liquid ocean beneath it, kept liquid by tidal heating from Jupiter's enormous gravitational pull. That ocean is dark. It has no sunlight reaching it through the ice. It may have hydrothermal vents on its floor. It may have organic chemistry, and it may have life. Enceladus, a moon of Saturn, shoots geysers of water ice from cracks near its south pole. Water that comes from a subsurface ocean that appears to contain the chemical ingredients for life. And Titan, Saturn's largest moon, has lakes and rivers and rain, not of water, but of liquid methane, chemistry so alien to us that we have barely begun to imagine what organisms adapted to it might look like. None of these possibilities would have seemed worth serious scientific attention before we learned what the Mariana Trench and the deep ocean have to teach us about the breadth of life's possibilities. The trench did not just change our understanding of the ocean, it changed our understanding of where in the universe we should be looking for the thing we are looking for. And we are barely looking at the trench. That is the paradox that lives at the heart of everything we have discussed tonight. Place that has the greatest potential to transform our understanding of life in the universe is also the place we have the least ability to study. Tools that would allow real, sustained, comprehensive exploration of the Mariana Trench either do not yet exist or exist only in prototype form and have not been tested at full trench depth. What would true exploration of the Mariana Trench look like? What would it take, host? It would take submersibles that could operate at full ocean depth, not for 3 hours, but for days. Vessels that could cover significant horizontal distances across the trench floor, rather than sitting in one spot. Vehicles with lighting systems, powerful enough to illuminate not just a 10-meter radius, but the full width of a section of the trench. Robotic arms with the dexterity to carefully extract core samples from the sediment without disturbing the surrounding area. Acoustic systems capable of creating detailed three-dimensional maps of the trench walls and floor to centimetre precision. It would take communication systems that could transmit data from the bottom of the trench to the surface in real time, so that scientists on the surface ship could participate in decision-making during the dive, rather than waiting for the vehicle to return and deliver data. It would take autonomous underwater vehicles, untethered robots capable of navigating the trench independently, and returning to a base station without human guidance. Some of these things are being worked on. The field of deep-sea robotics has advanced significantly in the years since Cameron's dive, driven partly by interest in deep-sea mining, which is an entire complicated and contentious story of its own that we will come to in a later part of this telling. Host. There are prototype autonomous and underwater vehicles that can reach Hadal depths and operate for extended periods. Crowd. There are new materials being developed that can withstand extreme pressure with less mass, allowing for smaller and lighter submersibles. Post. There are fibre optic communication systems that can transmit more data through tethers than was previously possible. But all of this is in early stages. All of it is expensive. All of it faces the fundamental challenge that every piece of equipment designed for the Hadal zone must be tested at Hadal pressures. And testing anything at Hadal pressures requires either a pressure vessel large enough to contain it on the surface, or an actual deep-sea dive. And both options are extraordinarily costly and technically demanding. The ocean does not make itself easy to study. It actively destroys the instruments we send into it. Corrosion. Biofouling, which is the colonization of equipment surfaces by marine organisms. The simple mechanical stress of deployment and retrieval through thousands of meters of water. The pressure, always the pressure, finding every weakness. Research instrument deployed at the bottom of the Mariana Trench has perhaps a few hours to a few days of functional life before the environment begins to degrade it. Against that backdrop, against the scientists who study the Hadal zone are doing something genuinely heroic. Host. They are trying to understand a place that does not want to be understood, with instruments that barely survive contact with it, on budgets that are a fraction of what would be needed for truly comprehensive work, in conditions that no human body can directly experience and survive. They are doing oceanography, with one hand tied behind their backs, standing at the edge of the deepest place on Earth, and trying to describe what they cannot see. And what they have found, even under those constraints, is extraordinary. The walls of the Mariana Trench, the near vertical cliffs of rock that rise from the floor to the rim, are covered in communities of organisms that are unlike anything found on the abyssal plain below or the ocean floor above. These communities are influenced by the specific geology of the trench walls, by the chemistry of fluids seeping through cracks in the subducting plate, by the unusual current patterns that develop within the confined geometry of the trench. Some areas of the trench walls appear to support chemosynthetic communities, ecosystems powered by chemical energy from within the earth rather than by the marine snow falling from above. Chemosynthesis, that word again, it is the key that unlocked so much of what we know about the deep ocean. where photosynthesis uses light energy to convert carbon dioxide and water into organic matter and oxygen. Chemosynthesis uses chemical energy, typically from compounds like hydrogen sulfide or methane, to do the same thing, and the organisms that perform chemosis and the organisms perform chemosynthesis are the foundation of food webs that need no sunlight at all, food webs that are powered entirely from within the Earth. In the Mariana Trench, there may be chemosynthetic activity associated with the subduction process itself. The diving Pacific Plate carries water-bearing minerals down into the mantle, and as the plate heats up under increasing pressure and temperature, water is released and migrates back upward through the overlying rock, carrying with it dissolved chemicals from the mantle. These fluids, where they seep through cracks in the trench walls, may support microbial communities that are processing mantle chemistry, that are eating, in a sense, the Earth's interior. If that is true, and the evidence suggests it may be, then the Mariana Trench is not just a hole in the ocean floor. It is a connection point between the surface biosphere and the deep interior of the planet, a place where the chemistry of the mantle meets the biology of the ocean, a place where the distinction between the living and the geological blurs in ways we are only beginning to perceive. And we have 3 hours of direct human observation. That is where we are tonight. Standing at the edge of the most profound ignorance humanity has about its own planet, looking down into darkness that has kept its secrets for 60 million years, knowing that the secrets are there, knowing that they are important, knowing that they change everything, and knowing that we do not yet have the means to reach them. But we are going to keep trying, because the trench is calling. It has always been calling. It has always been calling. Every scientist who has ever heard recordings of the sounds that propagate through the water column of the deep Pacific, the deep groans and low rumbles and strange clicking sequences that fill the Hadal acoustic environment, felt it. The sense that the deep is not silent, that the deep is speaking, in a language we do not yet speak, about things we do not yet understand. What is making those sounds? What moves through the darkness of the Mariana Trench in the spaces between our visits? What has been living there undisturbed for millions of years, in the cold and the pressure and the absolute dark? We will go further into that darkness in the next part of this story. But for now, let the question rest in you. Let it sit in your chest the way pressure builds as you descend, slowly, heavily. Something vast and dark and full of life that we have not yet named. Somewhere in that darkness, something is moving. The Mariana Trench makes sounds that no one has fully explained, low and vast and ancient, travelling through the water column like the breathing of something too large to see. Tonight we descend into those sounds and ask what is making them. We left you with a question hanging in the dark. Something is moving down there. Something fills the acoustic environment of the Hadal zone with signals that our instruments can detect, but our understanding cannot yet decode. Before we can talk about what those sounds might be, we need to understand something fundamental about the deep ocean that most people never consider. In the dark, where there is no light, sound is everything. We are creatures of light. Every organ you use to understand the world around you, your eyes, the way your brain builds maps of space by interpreting reflected light, evolved in a world saturated with photons. You think in light. You navigate in light. You recognize faces, read expressions, judge distances, all of it dependent on the electromagnetic radiation your star emits and your atmosphere permits to reach the surface. Take away the light, and you are, in a very real sense, lost. But the deep ocean creatures are not lost in the dark. They have never needed light in the way we need it. What they have instead is something older, something that travels farther and carries more information through water than light ever could. They have sound. Sound travels through water approximately 4 times faster than it travels through air. In air, sound moves at roughly 340 meters per second. In seawater, it moves at around 1500 meters per second, and that speed changes with depth, with temperature, with salinity, in ways that create something remarkable in the deep ocean. There is a layer in the ocean, sitting roughly between 300 and 1000 meters depth, depending on location, called the SOFA channel. SOFA stands for sound fixing and ranging. It is a layer where the speed of sound reaches a local minimum, depth, where the sound velocity is lower than both the warmer water above it and the more compressed water below. And in that channel, sound does not simply travel. It bounces. It is trapped. Low-frequency sounds entering the SOFA channel can travel thousands of kilometers, crossing entire ocean basins, losing very little energy, arriving at their destination as clearly as they left their source. Whales use this channel, blue whales, the largest animals ever to have lived on this planet, produce calls so low in frequency that you cannot hear them without equipment to slow them down and raise their pitch. These calls travel through the SOFA channel across thousands of kilometers of ocean. Blue whale, calling off the coast of California, can in principle be heard by another blue whale near Japan. The ocean is an acoustic world of extraordinary richness and connectivity, and we are only beginning to map it. Now descend below the SOFA channel, descend past the midnight zone, past the abyssal plain, down into the Haddle zone, down into the Mariana Trench itself. What sounds exist there? What fills the acoustic environment of the deepest place on Earth? Scientists lowered hydrophones, which are underwater microphones, into the Challenger Deep in 2015 as part of a project by NOAA, the National Oceanic and Atmospheric Administration. They expected perhaps a baseline of near silence, punctuated by geological sounds from the subducting plates. What they recorded was something far richer and far stranger than silence. They recorded the low moaning of earthquakes, deep seismic rumbles that travelled through the rock and into the water, filling the trench with a bass vibration that you would feel in your chest, more than hear with your ears. They recorded the sound of a magnitude 5 earthquake that occurred during the deployment, sound that propagated through the water column from a distant location, and arrived at the bottom of the trench as a long, complex wave of pressure. They recorded the passage of a typhoon at the surface, the churning of that enormous storm detectable as a low rumble 11 kilometers below, the surface world communicating its violence downward through the entire depth of the ocean. And they recorded biological sounds, songs of baleen whales travelling through the water from far away, audible even at the bottom of the trench, because sound in the deep ocean travels with so little loss. The clicks of ship propellers, from commercial vessels passing far overhead, sounds that were not immediately identifiable. Sounds that the researchers described as unknown biologics, which is the scientific term for sounds produced by a living organism that has not yet been identified. Unknown biologics in the Mariana Trench, sounds made by living things that we cannot name. This should not be surprising, given everything we have discussed. The trench contains organisms we have never identified, and it certainly does. Then those organisms are producing sounds. A host, whether those sounds are the product of their movement, or their feeding, or their communication, they are acoustic signatures of life forms we do not have in our catalogue, and we are recording them without knowing what we are recording. The researchers who analysed those Noah recordings described the experience as humbling in a way that their scientific language struggled to contain. A host. You are listening to an environment, one of them said in an interview, where you can detect the passage of a storm 10 kilometres above you and the earthquake happening hundreds of kilometres away, and something living right there nearby, making a sound you have never heard before and cannot explain, and the weight of how much you do not know becomes almost physically heavy. At the bottom of the Mariana Trench, even the things we can detect with our instruments remind us of the things we cannot understand. But the acoustic environment of the deep is not just mysterious. It is also being disrupted. The same commercial shipping that the hydrophones detected. The propeller noise of cargo vessels crossing the Pacific has increased dramatically over the past century. Ocean noise pollution from shipping, sonar, seismic surveys conducted by oil and gas companies and other industrial sources has measurably increased in frequency and intensity across the world's oceans. The low-frequency noise that travels farthest and most efficiently through the ocean, the noise that fills the Sofar Channel and propagates through the Hadal Zone, approximately doubled in intensity every decade since the 1950s. What does that mean for the acoustic world of the Mariana Trench? We do not fully know. We have not had the equipment in the trench long enough to establish the kind of long-term acoustic baseline that would allow meaningful comparison. But we know from studies of shallower ocean environments that noise pollution disrupts animal communication, interferes with navigation, causes stress responses in marine mammals and fish, can mask the acoustic signals that organisms use after food and mates. The deep ocean is not insulated from this. The sounds travel there. We are disrupting an acoustic ecosystem we have never heard properly. In a place we have never truly visited, let us step back from the acoustic world and return to the geology. Because the geological story of the Mariana Trench is inseparable from every other story about it. And there is one aspect of that geology that we have not yet fully explored, an aspect that has implications reaching far beyond the trench itself, an aspect that connects the Mariana Trench to events that shaped the history, life on Earth. Subduction zones like the Mariana Trench are responsible for one of the most important geological cycles on our planet, carbon cycle. Carbon is the basis of all life. Every living cell is built from carbon compounds. Carbon circulates through the Earth in a cycle that operates over millions of years, moving from the atmosphere to the ocean to the rock and back again. The carbon cycle is what regulates the Earth's climate over geological time, keeping the planet in a temperature range that allows it out liquid water and therefore life. The deep ocean floor is one of the major storage sites for carbon. Organisms in the surface ocean absorb carbon dioxide from the atmosphere through photosynthesis and build their bodies from it. When they die, some of that carbon sinks to the ocean floor as part of the marine snow, and some of it is incorporated into the sediment and eventually into the rock of the ocean crust. The subducting Pacific plate carries this stored carbon down into the mantle. In the mantle, the carbon is eventually released, typically through volcanic eruptions, returning to the atmosphere as carbon dioxide. This is the long-term geological carbon cycle, POST, operating on timescales of millions of years, and subduction zones like the Mariana Trench are the return pathway, point where surface carbon re-enters the deep Earth. Scientists studying the Mariana Trench subduction zone have recently discovered that more carbon is being carried into the mantle through this pathway than previously believed, and more water, and more of the organic sediment that contains the chemical signatures of ancient life. The trench is, in a very real sense, swallowing the record of its own ecosystem and sending it down into the Earth's interior. What happens to that carbon in the mantle? Some of it is returned through volcanoes, but some of it may remain in the deep Earth for hundreds of millions of years, sequestered in a form that neither the ocean nor the atmosphere can access. The Mariana Trench may be a net carbon sink, removing carbon from the surface accessible cycle and locking it away in the planetary interior on a timescale that dwarfs anything we can meaningfully conceptualize. If true, this has implications for how we understand climate and carbon budgets going back to the formation of the planet. And it means that the trench, even without any deliberate human action, is performing a kind of planetary service, a slow geological management of atmospheric chemistry that has been operating since the Pacific Plate began its long dive. A hole in the ocean floor, 60 million years old, governing the chemistry of the atmosphere, producing sounds we cannot explain, harbouring life forms we have not named, connected to the question of whether life exists elsewhere in the universe. Contaminated by our industrial chemistry without our ever visiting it, this is the Mariana Trench. This is what we have done so little to understand. Now let us talk about the history of the attempts, cause the history of human efforts to reach the bottom of the world is also the history of human ingenuity meeting its limits over and over, each attempt going a little further. Each attempt teaching a little more. Each attempt leaving behind something. Sometimes equipment, sometimes questions. Occasionally lives risked in ways that the rest of us watching from the surface can barely imagine. The first measurement, as we discussed, came from HMS Challengers in 1875. But the first real attempt to reach the bottom, to go there rather than simply measure, came from a very different kind of vessel nearly a century later. The Trieste was not a graceful machine. It was a bathyscaphe, a type of deep-diving vessel invented by the Swiss physicist Auguste Piccard, father of Jacques Piccard, who would eventually descend in it. The word bathyscaphe means deep ship in Greek. It worked on a principle borrowed from hot air balloons. Instead of being powered downward, which would require enormous energy against the resistance of the water, the Trieste was made heavy enough to sink on its own, carried 17 tons of iron shot, As ballast, pellets of metal held in place by an electromagnet. To descend, you simply released buoyancy. To ascend, you released the iron shot by cutting the electrical current to the electromagnet, and the remaining gasoline float provided the vessel's positive buoyancy, carried it back to the surface of the surface. It was elegant in its simplicity, astonishingly brave in its execution. Tossed on January 23rd, 1960, Jacques Piccard and United States Navy Lieutenant Don Walsh boarded the Trieste and began their descent into the Challenger Deep. The dive took nearly 5 hours. For 5 hours, these two men sat in a steel sphere, slightly less than 2 meters in diameter, walls 22 centimeters thick, watching the pressure gauges climb as the darkness thickened around them. No radio contact with the surface, GPS. No ability to know exactly where they were horizontally, only vertically. Only the pressure gauge telling them they were still going down. About 9,000 meters, a crack appeared in the outer plexiglass window of the entry tube, not the main observation sphere, but the access tunnel. And it produced a sound like a rifle shot that echoed through the metal of the vessel. Walsh and Piccard looked at each other. They considered turning back. They decided the crack was in a non-critical component and continued. Think about that decision. 9,000 meters down, a crack in the hull material. An hour of descent still to go. No rescue possible, and they decided to continue. At 10,916 meters, the Trieste settled onto the floor of the Challenger Deep. Piccard later wrote that the bottom appeared brown and diatomaceous, meaning it was made of the tiny shells of microscopic organisms. Through the viewport, in the lights of the Trieste, he saw something moving. That flatfish, or whatever it was, drifting along the floor of the deepest place on Earth. They stayed at the bottom for 20 minutes. 20 minutes. Preparation for the dive took months. The engineering work that made the Trieste possible took years. Theoretical work behind it represented decades of scientific thinking. And the time actually spent at the bottom place that all of that effort was aimed at reaching was 20 minutes. Walsh was once asked whether he felt disappointed by how little time they had at the bottom. He said, no. He said that 20 minutes at the bottom of the Mariana Trench in 1960, with the technology of that era, was not a failure, miracle. It was the proof that it could be done, and that was the most important thing. Everything else, the longer dives, the better instruments, the more detailed observations, those could come later. In 1960, all that mattered was proving that a human body could reach the bottom of the world and return to tell about it. They returned. Crack in the access tunnel did not fail. The electromagnet held until they were ready to ascend, and when they cut the current, the iron shot fell away, and the Trieste rose, slowly, over 3.5 hours. Back through the midnight zone, back through the twilight zone, back into the sunlit water, back to the surface, back to the world. And then the world more or less forgot about the Mariana Trench for 50 years. That is perhaps the strangest part of this story. The greatest depth of ocean, the deepest point on Earth, reached by human beings for the first time in 1960, and then essentially abandoned as a scientific priority for the next half-century. No manned return until James Cameron in 2012. 52 years. Why? The reasons are practical and political and economic all at once. The Cold War directed enormous scientific and engineering resources toward space, toward the race to the moon that captured global imagination, global exploration, in a way that ocean exploration simply could not compete with. Cost of deep ocean exploration was enormous, and the immediate practical returns were difficult to quantify. The military which was interested in submarines and deep-water acoustics for strategic reasons, conducted some classified research at depth, but the results were not shared with the scientific community. And the sheer technical difficulty of the problem meant that progress was slower than the pace needed to maintain political and financial interest. Space is more legible than the deep ocean. Space is visible. You can look up and see the moon and imagine going there. The deep ocean is invisible, hides beneath the surface of a featureless grey-blue expanse, and nothing about looking at it from a ship conveys any sense of what is below. Space exploration produced images, magnificent images, of planets and nebulae and astronauts floating free of the Earth that fired the public imagination. The Mariana Trench produced from Pickard and Walsh's dive a description of brown sediment and a possibly imagined flatfish was not the stuff of popular legend, not yet. But the scientists who understood what the trench represented, kept working. Unmanned, remote, slow. Baited traps and dredged nets and acoustic sensors lowered on cables from surface ships, pulling up samples that each told a fragment of a story that the trench was not making easy to read. And each fragment was astonishing. In the 1980s, as the ban on PCBs was being implemented, and scientists were beginning to understand the global reach of persistent organic pollutants, the first sediment cores from the Mariana Trench were being analysed. They showed something that no one had quite expected. The sediment of the trench was layered like a geological archive, each layer representing a different period in the Earth's history, each layer containing the chemical and biological signatures of its time. Fossil foraminifera in the sediment recorded ancient ocean temperatures. Chemical ratios in the minerals recorded ancient ocean chemistry. Isotopic signatures in organic compounds recorded the biological activity of oceans that no longer existed. The trench is not just a hole, it is a library, an archive. A record of the Pacific Ocean stretching back millions of years, preserved in the cold and pressure of the Hadal Zone, better than it is preserved almost anywhere else on Earth. And like the rest of the trench, we have read only the first few pages. In the 1990s, the Japanese remotely operated vehicle Kaiko became the second vessel, after the Trieste, to reach the full depth of the Challenger Deep. Kaiko was a completely different kind of machine from the Trieste. It had no crew. It was controlled from the surface via a fibre optic tether, receiving commands and sending back video in near real time. It could move horizontally, sample the sediment, could observe and record in ways that the Trieste simply could not. It made multiple dives to the Challenger Deep over several years, collecting sediment, samples and video footage data that gave scientists their first extended look at the trench floor. And then, in 2003, while being recovered after a dive in a different location, Kaiko was lost. A tether connector failed in rough seas during recovery, and Kaiko, the only vehicle then capable of reaching the full depth of the Challenger Deep, sank back into the ocean and was never recovered. Japan spent years building its replacement. Kaiko Mark II, and the Challenger Deep went again without a visitor. The pattern repeats. We build, we reach. We lose something, we build again. The trench takes our instruments and we start over. And in the meantime, the trench continues. Its 60 million year indifference to our schedules. There is something the trench seems to demand of anyone who wants to understand it. Patience beyond the normal human scale, willingness to invest years in building something that may be destroyed in moments. The acceptance that the answer you are seeking will not come from one expedition or one instrument or one set of samples, but from a long, slow accumulation of fragments, each expedition adding a small piece to a picture so large that no single scientist, perhaps no single generation of scientists, will ever see it whole. That kind of patience is not natural to our species. We are built for quick returns. Our brains are wired for the satisfaction of problems solved and questions answered. The Mariana Trench offers neither. It offers questions that expand as you approach them, mysteries that deepen rather than resolve, an environment that resists every attempt at systematic study, with a physical obstinacies that feels at times almost intentional. The scientists keep going, and the data keeps accumulating. And slowly, so slowly that the progress is almost invisible. From year to year, picture is forming. We know that the trench floor is not uniformly flat. There are ridges and valleys within the Haddle Zone itself, variations in depth and topography created by the irregular geometry of the subducting plate. We know that the sediment is not uniformly deep. In some areas it is meters thick. In others it is thin or absent, and bare rock is exposed. Rock that tells a different story from the sediment about the geological history of this place. We know that the water chemistry of the trench is not uniform either, that there are gradients in oxygen concentration and chemical composition that create microhabitats within the Haddle Zone. Small patches of different conditions that support different communities of organisms. The trench is not a single environment. It is a collection of micro-environments, each one with its own character, its own chemistry, its own community of life. And we have sampled in total a tiny fraction of those micro-environments. We have no idea how many more there are. We have no reliable estimate of the total biodiversity of the Haddle Zone, because we have not looked nearly enough of it to extrapolate meaningfully. Time we look, we find new. In 2016, a research vessel dropped a baited camera to the floor of the Mariana Trench and recorded snailfish at depths previously thought impossible for any fish. In 2019, another expedition found communities of organisms near what appeared to be weak chemosynthetic fluid seepage on the trench walls, the first indication of possible chemosynthetic biology within the trench proper, rather than at surface hydrothermal vents. In 2022, the record for deepest fish was broken. The snailfish filmed at 8,336 meters, and the researchers noted the presence of multiple individuals, suggesting a population rather than an isolated individual, or a population bottom of the world, living their entire lives in the dark, under 1,000 atmospheres of pressure, in near freezing water, eating amphipods and breeding and dying, and their descendants doing the same. Generation after generation, for millions of years. What does a million generations of darkness do to a lineage? What does a million generations of pressure, of cold silence, broken only by seismic groans and the distant echoes of surface storms, what does that do to the biology and the behaviour and whatever passes for the internal life of a creature? We cannot know. We do not have the access. We do not have the time. We have 3 hours of direct human observation, and a handful of baited camera deployments, and a small library of sediment cores, and from that, we are trying to understand a world that has been doing its own thing in its own way for 60 million years without us. Humility that requires is immense, and it is, in its own way, beautiful. Because the trench does not need us to understand it. The snailfish does not require our knowledge to go about its life. The amphipods swarming over a piece of bait in the deepest dark are not waiting for our description of them. The xenophyrophores growing to the size of softballs on the trench walls are not diminished by our ignorance of their biology. The trench existed before there were human brains to perceive it, and will exist long after the last human brain has quieted. We are the ones who need the understanding. We are the ones diminished by the ignorance. We are the ones with something to gain from every fragment of knowledge we pull at great cost and effort from the dark. And that need, that reaching toward the bottom of the world for knowledge that is hard and expensive and slow to extract, is one of the most distinctly human things there is. No other organism on Earth has looked at the Mariana Trench and thought, I want to understand that. And no other organism has designed a pressure sphere and spent months engineering a vehicle and risked its life descending in steel bubble into the deepest place on the planet in pursuit of understanding. We do that, only us. And the trench accepts our visits, briefly, on its own terms, and gives us small pieces of itself, and takes back most of what we bring down, and we go home and study what we have, and then we build something new, and go back. There is a next chapter to this story, Host. There is a development in the exploration of the Mariana Trench that is happening right now. In the years around the time you are listening to this, that changes the equation in ways both hopeful and troubling. A new set of interests has turned its attention to the deep ocean, interests that are neither purely scientific nor purely exploratory, interests that have the funding and the engineering capacity to go deeper, and more often than any research institution could afford. And what those interests want from the deep ocean is not understanding. What they want is something else entirely. Something that lies in the sediment of the deep ocean floor, in quantities that have caught the attention governments and corporations and engineers around the world. Something that the Mariana Trench and the abyssal plains around it holds in abundance. And the story of what that is and what pursuing it might mean for the deepest and least understood ecosystem on our planet, where we are going next. But for now, the trench is breathing in the dark beneath you. The sounds are there, travelling upward through 11 kilometres of cold water, the earthquake, rumbles, and the whale songs, and the unknown biologics making their unidentifiable signals in the absolute dark. Something pale is drifting just above the sediment, its translucent body catching nothing because there is nothing to catch. No light anywhere, only the faint chemical signals of food drifting on a current from somewhere above, and deep in the sediment, in the cold and the pressure, the microbes are processing. They have been processing for 60 million years. They will continue long after this night is over, long after every instrument we have ever sent down there has corroded to nothing, long after the questions we are asking tonight have been answered and replaced by questions we have not yet thought to ask. Trench holds its secrets carefully. But one by one, very slowly, with enormous effort, we are learning to listen. The Mariana Trench and the ocean floor around it, and the oceans hold something that the modern world wants very badly, something locked in the sediment and crusted onto the ancient rock in quantities that have set governments and corporations moving toward the deep with an urgency that no scientific curiosity alone has ever produced. And tonight we follow that urgency down into the dark and ask what it will cost. We left you with a shadow on the horizon, a new kind of interest turning its eyes toward the bottom of the world. Not the quiet, patient interest of a scientist lowering a baited camera on a long cable and waiting. Something faster, something louder, something with shareholders and quarterly reports and the weight of industrial civilization behind it. To understand what that interest wants, you need to understand something about the geology of the ocean floor that most people have never heard of, scattered across the abyssal plains of the Pacific, including the plains that surround the Mariana Trench. There are objects called polymanalic nodules. They are roughly potato-shaped, ranging from the size of a marble to the size of a grapefruit, and they lie on the surface of that sediment in fields that stretch for hundreds of kilometers. Some areas of the Pacific abyssal plain are so densely covered with these nodules that the ocean floor looks, from the camera of a deep-sea vehicle, like a field of dark cobblestones. They form over millions of years, accreting layer by layer around a tiny nucleus. A shark tooth, fragment of shell, a piece of volcanic rock, as minerals precipitate slowly out of the surrounding seawater, grow at a rate of roughly 1 to 2 millimeters every million years. That is not a typo. 1 to 2 millimeters per million years nodule. The size of a golf ball may have been growing for tens of millions of years, and inside them, concentrated by that incredibly slow process of precipitation, are metals: manganese, nickel, cobalt, copper, and in smaller but significant quantities, rare earth elements and other metals that the modern world uses, in quantities that are rapidly outpacing the supply available from conventional land-based mines, the batteries in electric vehicles, the electronics in smartphones, the components in wind turbines and solar panels, and the entire technological infrastructure of the energy transition that the world is currently attempting. All of these require cobalt, nickel, manganese, rare earths, crowd, and the land-based deposits of those metals are concentrated in a small number of countries, making supply chains vulnerable and politically complicated. The deep sea nodule fields of the Pacific contain, by some estimates, more manganese, cobalt, and nickel than all the known land-based reserves combined. The Clarion-Clipperton Zone, an enormous area of abyssal plain between Hawaii and Mexico, has been surveyed in more detail than almost any other part of the deep ocean floor, specifically because of its nodule deposits. And the waters around the Mariana Trench sit at the edge of regions that mining companies and national governments have been quietly studying for decades. There is also another type of deposit that interests the mining industry even more in some ways: cobalt-rich ferromanganese crusts. These are not nodules scattered on the sediment, but coatings on the surface of seamounts and the rocky walls of underwater ridges, including the walls of the Mariana Trench itself. These crusts can be several centimetres thick, built up over millions of years, rich in cobalt, at concentrations several times higher than the best land-based cobalt ores. The walls of the Mariana Trench, those near vertical cliffs of ancient rock that rise from the deal floor, are coated in places with crusts that represent, to a mining engineer, significant economic resource. To a marine biologist, those same crusts are something else entirely. They are habitat. The organisms that live on the trench walls, the communities of corals and sponges and microbial mats and specialised invertebrates, many of them unknown to science, live on and in those crusts. Their communities have developed over millions of years in direct relationship with the chemical and physical properties of the crust surface. Remove the crust, and you do not just remove a mineral deposit. You remove an ecosystem that grew at a rate of a few millimetres per million years. An ecosystem that, once destroyed, cannot recover on any timescale that is meaningful to human civilization. Not in 100 years, not in 1,000, not in 10,000. Recovery timescale for deep sea mining disturbance, based on the limited evidence available from past experimental dredging in the deep Pacific, is measured in millions of years. Scientists studying the tracks left by experimental dredging in the Clarion-Clipperton zone in the 1970s, tracks made by equipment, dragged across the nodule fields as a test of mining feasibility, turned to those sites in the 2000s and found that the tracks were still there, undisturbed. The sediment had not recolonized, the organisms had not returned. After 30 years, the tracks looked essentially as they had the day they were made. The ecosystem there did not recover on a human timescale because it did not grow on a human timescale. Creatures that live in the deep abyssal environment, the nodule-dwelling organisms, the sediment in fauna, the suspension feeders on hard rock surfaces, grow and reproduce so slowly that disturbance simply persists. This is the central conflict of the deep sea mining debate, and it is a conflict that is directly relevant to the Mariana Trench and its surroundings. On one side is the genuine material need of the energy transition, the reality that the world needs enormous quantities of certain metals to build clean energy infrastructure that may be necessary to avoid the worst consequences of climate change. On the other side is the reality that the only way to get those metals from the deep ocean is to destroy environments that took tens of millions of years to develop and that we have barely begun to understand. Environments that may harbour undiscovered life, unknown chemistry, biological innovations with medical and scientific implications we cannot yet anticipate. This is not a simple debate. People who argue for deep-sea mining are not villains. They are responding to real pressures, real material needs, real supply chain vulnerabilities. And the people who argue against it are not naive idealists. They are responding to real science, real data about the fragility of these ecosystems and the permanence of the damage that extraction would cause. And And hovering over this debate, central to it, is the fact that we do not know enough about the deep ocean to fully evaluate either argument. We do not know what we would be destroying. We do not know which organisms live in those nodule fields and crust habitats, what ecological role host, what ecological roles they play, what chemical compounds they produce, what secrets their biology might contain. We are being asked to make a decision about whether to mine environments that have never been properly surveyed, in a place we have barely visited, on the basis of economic models built largely on data we collected from the surface. It is a bit like being asked to decide whether to demolish an ancient library to build a car park without having been allowed to read any of the books first. The library might contain nothing of practical value, or it might contain knowledge that changes everything. We do not know. And we are being asked to decide before we find out. The International Seabed Authority, an organization established under the United Nations Convention on the Law of the Sea, governs the regulation of deep-sea mining in international waters. It has been developing a mining code, set of regulations that would allow commercial deep-sea mining to proceed while supposedly protecting the most sensitive ecosystems. The process has been contentious and slow, with some member states pushing for rapid development of mining regulations to facilitate industrial activity, and others, including a growing coalition of nations calling for a moratorium on deep-sea mining, arguing that the science is nowhere near sufficient to allow responsible regulation of an activity with such potentially irreversible consequences. Mariana Trench itself, the Challenger Deep, the Challenger and its immediate surroundings, sits within the exclusive economic zone of the United States, which administers it through the Mariana Trench Marine National Monument, established in 2009 past. This designation provides some protection for the trench itself from direct space exploitation, but the abyssal plains surrounding the trench, the nodule fields and crust-covered seamounts in the international waters nearby are under the governance of the International Seabed Authority and are the subject of exploration licenses held by companies and national governments, intentions that are clearly commercial. So the trench exists in a strange position, partly protected, partly surrounded by areas where the debate over exploitation is unresolved. A monument at the centre of a resource frontier, and in the middle of this geopolitical and environmental complexity, the science continues. Because the same engineering developments that are being driven by mining interest, the need for vehicles that can operate at depth for longer periods, low periods that can cover more ground, that can collect more varied samples, is also advancing the capabilities of scientific exploration. The industrial interest in the deep ocean, paradoxical as it seems, has contributed to improvements in deep-sea vehicle technology that benefit scientific research. Full ocean depth vehicles that have been developed in the past decade, submersibles capable of reaching any point in the world's oceans regardless of depth, represent a genuine step change in deep-sea exploration capability. The submersible limiting factor, built by the company Triton Submarines for the 5 Deep expedition, completed dives to the deepest point in each of the world's 5 oceans between 2018 and 2019. including multiple dives to the Challenger Deep. These were not single historic dives like Pickard and Walsh or James Cameron. These were systematic, repeated dives, demonstrating that the Challenger Deep be visited not as in a generation feat, but as a routine, repeatable operation. The Five Deeps expedition produced more hours of direct human observation at full ocean depth than all previous dives combined. And in those hours, the explorers found, among other things, a plastic bag and candy wrappers on the floor of the Challenger Deep. Plastic. Packaging. Detritus of the surface world. Sitting on the floor of the deepest place on Earth. Not as a chemical trace in the bodies of amphipods, not as microplastic fragments as in a sediment core, as recognizable intact pieces of human garbage lying in the mud 11 kilometers below the ocean surface. The team that found them described a complex emotional experience, satisfaction of having reached a place that so few humans had ever seen, mixed with the profound dismay of finding that humanity had been there before them in the worst possible way. Reach the bottom of the world and find our litter. You travel to the most remote place on the planet and discover that we have already marked it. There is no wilderness left. Not truly. There is no place on this earth where the human footprint is absent. And that reality, stark and unavoidable, in the form of a plastic bag on the floor of the Challenger Deep, changes something in how we think about the Mariana Trench and what we owe it. Because if we have already altered it, already contaminated it, already left our garbage in its deepest corner, then the argument that it is a pristine wilderness that must be preserved unchanged becomes, in a narrow technical sense, inaccurate. It is not pristine. We have already changed it, and that fact could be used, cynically, to argue that further intervention, including mining, is not adding insult to injury, but simply continuing a process already underway. That argument would be wrong. Deeply wrong. And here is why. The contamination that has reached the Mariana Trench so far, the PCBs, microplastics, the isolated pieces of garbage, is the unintentional consequence of surface activity. It arrived at the trench via the same pathways that carry marine snow, slowly, diffusely, over decades, bossed in concentrations that are measurably harmful, but that the ecosystem of the trench has at least had some time to encounter, if not adapt to. It is damage. It is real damage, but it is passive damage. Deep-sea mining would be active damage, physical, immediate. Mining machine operating on the trench walls or the surrounding abyssal plains would not leave traces. It would leave craters, paused, roared. It would remove the surface layer of the sediment, the layer where most of the biology lives. It would generate enormous sediment plumes, clouds of fine particles stirred up by the mining machinery that would drift for hundreds of kilometers and settle over undisturbed areas, smothering the organisms there. It would produce noise at intensities and frequencies that the deep-sea acoustic environment has never experienced before. It would create chemical changes in the water column as the disturbed sediment releases its stored compounds. The scale of industrial deep-sea mining, if it proceeds, would be unlike anything the Hadal Zone has ever encountered, and unlike the slow contamination we have already inflicted, it would not give the ecosystem even the meagre time it has had to encounter the change. it would happen at the speed of industrial machinery. And once the nodules are gone, they are gone. Not for a human lifetime. Not for a geological era. They are gone. A nodule field that took 30 million years to develop, once mined, does not begin to recover on any timescale relevant to any organism currently alive on this planet, including us. Scientists studying the biology of the nodule fields have found that the nodules themselves are habitat. Organisms live on them, in them, around them. The surface of a nodule, examined under a microscope, reveals a dense community of microbes and tiny invertebrates, living in the pits and crevices of its surface. These communities are not the same as the communities that live in the surrounding sediment. They are distinct. They are specialized. They exist only because the nodule exists. Remove the nodule, and those communities go with it. In the Clarion-Clipperton Zone force, which is the most studied nodule field, because it is the most targeted for mining, scientists have catalogued thousands of species in the course of recent surveys. A large fraction of them were new to science. Unknown, named for the first time in the papers reporting their discovery, and the surveys are not complete. Every survey finds new species, every baited trap, every sediment core, every rock sample comes back with organisms that have never been described before. We are discovering the library even as we debate whether to demolish it. Some of what is in that library is extraordinary in ways that go beyond scientific classification. The chemistry of deep-sea organisms evolved under conditions that produce biological innovations unavailable to surface life, is a source of compounds with potential applications in medicine, in biotechnology, in materials science. Deep-sea microbes have already yielded enzymes used in biotechnology, including enzymes used in the polymerase chain reaction process, the PCR test, which you may have encountered during the pandemic years. That technique, which has saved countless lives and enabled countless scientific advances, depends on an enzyme originally isolated from a bacterium found in a hot spring, a hydrothermal vent ecosystem related to those in the deep ocean. What else is in those deep-sea organisms? What compounds remain undiscovered in the cells of Hadal amphipods, biochemistry of trench floor microbes, in the tissue of the snailfish that solved the pressure problem in ways our engineers are still trying to understand? We do not know. We cannot know until we look, and we cannot look if we have destroyed the library. This is the argument that drives marine biologists and conservation scientists to their keyboards and their podiums and their testimony before international bodies. Not sentiment, not aesthetics, not the vague feeling that wilderness should be preserved because wilderness is beautiful. Hard, practical argument that the deep ocean is a source of biological knowledge and chemical innovation that has not yet been accessed, that cannot be accessed after it has been destroyed, and that may prove to be among the most valuable scientific resources on the planet. Against that argument, the demand for cobalt and nickel and manganese presses with the weight of the entire modern economy. There is no easy resolution, but there is a path that some scientists and policymakers are advocating, a path that threads between the two imperatives, without fully satisfying either. It is the path of comprehensive scientific survey before any mining, before a single mining license is acted upon, before a single machine descends to the deep for extraction. Survey the areas in question, catalogue the biology. Identify the most sensitive and the most biodiverse areas and protect them absolutely. Understand the sediment plume dynamics well enough to predict where mining disturbance will spread. Understand the recovery timescales well enough to evaluate what permanent loss means in specific locations. It is the argument of looking before you leap, of reading at least some of the books before you tear down the library. And for this argument, for every argument about what the deep ocean is and what it contains and what we owe it, the Mariana Trench stands as the central symbol, the deepest point, the most extreme environment, the place where the Hadal zone reaches its ultimate expression. We cannot protect properly. Study the deepest place on Earth, the place with the most extreme conditions, the place least accessible to industrial exploitation, simply because of its depth and difficulty. Then there is very little hope for the rest. Mariana Trench is in this sense a test. Not of our engineering, not of our technology, or our courage, or our institutional capacity, test of our wisdom, of whether we can hold something vast and unknown in sufficient respect what to learn from it, before we decide what to do with it. So far, we have passed that test only because the trench has been its own best protector. Its depth, its pressure, its cold, very properties that make exploration so difficult have also made exploitation impossible. The engineering challenges that have kept scientists from truly exploring the trench have kept miners from it too. But the engineering is improving. The costs are falling, the vehicles are getting better, and the demand for the materials in the deep ocean is not declining. If anything, it is rising as the energy transition accelerates, and the scale of the required battery chemistry becomes clearer. The window in which the Mariana Trench surrounding deep ocean around deep ocean can be properly studied before the pressure to exploit it becomes irresistible, may not be large, and the work that needs to be done, the comprehensive biological and chemical and geological survey of the Hadal zone that would, and allow genuinely informed decisions about its future, would require resources and time that are currently not being committed at the necessary scale. This is where we are tonight. At a threshold, at a moment when the choice is being made about the deep ocean, committee rooms and corporate boardrooms and the chambers of international bodies will determine what the deep ocean looks like for the next million years. And most of the people making those choices have never seen the deep ocean, never heard its sounds, have never held in their hands a sediment core from the bottom of the world and understood what it represents. They have never gone down. And the organisms at the bottom of the Mariana Trench, the snailfish and the amphipods and the xenophyophores and the pale microbial communities processing mantle subchemistry in the crack of the subducting plate. They know nothing of these decisions. They live as they have always lived, in the cold and the dark and the pressure, doing what they do, being what they have evolved to be over millions of years. Entirely indifferent to the debates happening 11 kilometers above them. They were there before we were. They will be there after us if we leave them in peace. The question is whether we will. Darkness of the trench holds that question, the way it holds everything, quietly, without in the cold, without urgency, without judgment, patience, that makes our entire civilization feel like a brief flickering of light in an enormity of dark. And above the trench, on the surface of the Pacific, the stars are coming out. And down below, in the absolute dark of the Hadal zone, something is drifting, something pale, something that does not know the word for darkness because it has never known anything else. Something that has never seen a star, never felt warmth, never heard a sound that was not a rumble from within the earth or the distant echo of a storm. Something ancient, something patient, something that belongs to a world that was old before we were young. And it drifts on undisturbed in the silence between worlds. The Mariana Trench has held its silence for 60 million years, and tonight, the end of this long descent through everything we know and everything we do not know about the deepest place on Earth, we arrive at the bottom together, and we rest here for a while, in the dark, in the cold, in the stillness that exists 11 kilometers below everything familiar. This is the final part of the story. Not because the story ends here. The story of the Mariana Trench does not end. It has no ending we can see from where we stand. But this is where we stop descending and simply float, suspended in the dark water, and let everything we have learned settle into us the way sediment settles to the floor of the Hadal zone. Slowly, without rushing, particle by particle. We have come a long way tonight. We started at the surface, at the question, why can we not truly explore the Mariana Trench? And we went down into that question the way the Trieste went down into the Challenger deep. Slowly, in stages. Each stage revealing something that the stage before it only hinted at. We found the pressure. 1,000 atmospheres pressing in from every direction. The weight of a column of water, 11 kilometers tall, sitting on every square inch of everything that tries to exist at the bottom. We found the darkness. Absolute, older than our species. Darkness that has never once been interrupted by natural light. Only by the brief and feeble glow of our submersible lights and the bioluminescent sparks of organisms making their own tiny fires in the enormous dark. We found the engineering failures, cracked hull of the Trieste at 9,000 meters, the lost manipulator arms of the deep-sea Challenger, the implosion of the ROV Nereus, loss of Kaiko in rough seas during recovery, the pattern of machines built and deployed and destroyed over and over, the ocean taking them back as if it does not wish to be studied too closely. We found the life, the snailfish, pale and translucent, bones, soft, and its body, mostly water, drifting above the sediment at depths that should be impossible for anything with a spine. The amphipods swarming in their thousands over a piece of bait in the absolute dark, enthusiastic and alive in conditions that would kill us in moments. The xenophyrophores, single cells the size of softballs, the largest single-celled organisms on Earth, going about their incomprehensible lives on the trench walls. The microbes in the sediment, processing ancient chemistry, growing better under 1,000 atmospheres of pressure than they do at normal. Pressure. Pisophiles, pressure lovers, organisms so perfectly matched to the most hostile environment on the planet that the hostility is simply their home. We found the contamination. The PCBs from industrial processes banned decades ago concentrated in the bodies of amphipods at the bottom of the world, microplastics in the sediment and in the flesh of Haddle creatures. The plastic bag and candy wrappers lying in the mud of the Challenger Deep, found by explorers who had travelled further from the ordinary world than almost any human before them, and discovered that the ordinary world had gotten there first. We found the sounds, the seismic rumbles of the subducting plate, the distant songs of whales travelling through the Sofar Channel, the unknown biologics, sounds produced by living organisms we have not yet identified, filling the acoustic environment of the Haddle Zone with signals we can record but not yet read. We found the geological story, the Pacific Plate diving beneath the Mariana Plate at a few centimetres per year for 60 million years, trench deepening imperceptibly as the Earth continues eating itself at this ancient boundary. The carbon being carried down into the mantle, the water being carried down into the mantle, the accumulated chemistry of the surface things, ocean being slowly incorporated into the deep interior of the planet. The trench as a passage between the surface world and the interior of the Earth. A doorway through which the chemistry of the ocean becomes, millions of years, the chemistry of the rock. We found the economic pressure, polymetallic nodules, the couture, growing at 2 millimeters per million years on the abyssal plains surrounding the trench, carrying cobalt and nickel and manganese in concentrations that the modern world wants very badly. The ferromanganese crusts on the trench walls, millions of years in the making, habitat for communities of organisms we have not yet catalogued. The mining debate, unresolved, pressing forward with the weight of industrial demand behind it, and we found the question that sits beneath all the other questions, the question that the Mariana Trench asks of us every time we try to approach it. Are we wise enough? Are we wise enough to hold something vast and unknown in sufficient respect to learn from it, before we decide what to do with it? Enough to invest in the slow, expensive, unglamorous work of comprehensive scientific survey before we commit to actions whose consequences will persist for millions of years? Are we honest enough to admit that what we do not know about the deep ocean far outweighs what we do know, and that the appropriate response to that ignorance is not boldness but caution? These are not comfortable questions. They do not have clean answers. They require a kind of intellectual humility that is difficult for a species that has spent its entire existence solving problems by acting on them, by building and digging and extracting and changing, by treating the unknown as a challenge to overcome rather than a presence to understand. The Mariana Trench does not respond to that approach. It has received our boldest attempts and returned them damaged or not at all. It has taken our best machines and found their weaknesses. It has accepted our 3 hours of direct human observation over 60 million years of existence and continued on exactly as before, indifferent to the visit, unimpressed by the effort. The trench is not waiting for us to conquer it. It is not even waiting for us to understand it. It is simply being what it is. The deepest place on Earth, the oldest wound in the ocean floor, the home of organisms that have solved problems we have not yet learned to ask. In a darkness that has its own kind of completeness, and what it asks of us. If we are willing to listen in the quiet way that listening is possible tonight, is not conquest, not extraction, not the bold planting of flags and the claiming of records. A What it asks is something much harder for us to give: stillness, the willingness to approach without immediately touching, the willingness to look without immediately taking, willingness to be in the presence of something enormous and unknown, and to feel the wonder of that without immediately converting the wonder into plan. That kind of stillness is rare for our species, but we are capable of it. On our best days, in our best moments, capable of standing at the edge of the unknown and simply being grateful that it exists. Tonight is one of those moments. Tonight, you have stood at the edge of the deepest place on Earth and looked down into it, and you have heard about what is there, and what we have done to it, and what we hope to learn from it, and what we risk losing before we learn it. And that knowledge, however partial, however incomplete, is a form of contact with a world that almost no human being ever directly experiences. Been, in the most real sense that imagination allows, to the bottom of the Mariana Trench tonight. Let us go there one more time, together, slowly. Picture surface of the Pacific Ocean, somewhere west of Guam. It is night on the surface too, and the stars are extraordinary here, far from any city. The Milky Way, a dense river of light across the black sky, reflecting in the dark water below. The ocean is not flat, it breathes. Long, slow swells move across its surface from some distant storm, and the water rises and falls with a rhythm that has been operating for as long as there has been an ocean. Below the surface, the light dies quickly. In the first 10 meters, it is still recognizable as light. In the first 100 meters, it has become a dim blue glow, directionless, softening. By 500 meters, it is essentially gone, faint luminescence, almost imagined, that fades completely before you reach 1,000 meters. And then the dark begins in earnest, passing through the midnight zone. Now, your body, if you were here, would already have stopped. The pressure at this depth, 2,000 meters, would have compressed the air spaces in your lungs and sinuses and collapsed them. Cold would have begun to pull the warmth from your body. But in your imagination you pass through, weightless, unhurt, ghost of attention drifting downward. The bioluminescence is everywhere. You cannot see the whole picture because your eyes are at the center of it, and what surrounds you in every direction is dark. But as you drift, creatures light up near you and fade. A jellyfish, its bell pulsing with a soft blue-green glow, passes to your left, trailing its long transparent tentacles behind it like a veil. Something smaller, too fast to follow, draws a bright blue line across your field of vision and is gone. Ahead and below, a chain of small lights pulses in sequence. Lanternfish maybe, siphonophores, those colonial creatures that string themselves together like living garlands across the midnight zone. The sounds here are different from the surface. Lower, longer. There is a presence of low-frequency sound that you feel more than hear. Vibration in the water that seems to come from no particular direction, but from everywhere at once. Collective acoustic presence of an ocean, full of life and geology and distant weather. You keep going down. Bioluminescence becomes sparser as you descend through the abyssal zone. The creatures here are fewer and more spread out. The water is colder. Pressure is enormous, though you do not feel it in the way you would feel it. The floor of the abyssal plain passes below you grey expanse as of fine sediment stretching away in every direction, dotted with the dark shapes of polymetallic nodules scattered like ancient fruit across the floor of a dead orchard. Sea cucumbers move across the sediment below, their pale bodies almost transparent, their motion so slow it registers only if you watch long enough. A brittle star, its 5 arms extended like a delicate star of living glass, filters the water above the sediment with a patience that seems, from the outside, indistinguishable from stillness. Everything here moves slowly. Everything here has learned that speed costs energy, and energy is scarce. The economy of the deep is a minimal economy. Every calorie precious, every movement deliberate. There is nothing wasted here, nothing spent on anything that does not serve survival. You continue to descend, and now the abyssal plain drops away as you cross the rim of the trench. The floor falls away below you, and you are floating above the huddle zone, above the 6,000 metre boundary, and the trench walls rise on either side. They are not sheer cliffs, not perfectly vertical, but close, rocky, ancient, coated in places with the dark rind of ferromanganese crust, studded in others with the white and orange and cream of cold water coral, communities that have been building their calcium carbonate structures in the dark for thousands of years. The water is colder here, pressure is immense. But you drift down, past the coral communities, past the crusts, past the bare rock where ancient lava flows from 60 million years ago were caught in the Earth's memory and have sat unchanged in the cold and pressure since before our species had a name for anything. The trench narrows slightly as you descend. The walls converge toward the bottom, the geometry of the Haddle zone closes around you, and the dark, already absolute, seems somehow denser, more textured, more present than the floor. It appears below you as a barely darker darkness at first, and then your eyes, or the eyes of your imagination, begin to resolve it. The sediment, fine as powder, brown-grey in the absent light, though there is no light to colour it. Flat, still, stretching away in the narrow valley of the trench floor, in both directions, into a dark your imagination can place there, but cannot truly fill. You settle toward it slowly, and as you near the bottom, as the first wisps of disturbed sediment drift up to meet you, something moves at the edge of your perception. Something pale. Something that holds its shape loosely, like water holding the shape of something that was once there. It drifts above the sediment with a motion that is barely motion, series of almost imperceptible fin movements that maintain its position in the slight current flowing along the trench floor. A snailfish. Body is translucent enough that you can see the dark line of its spine inside it, shadow of its internal structure visible through its own skin. Its eyes are small, set wide apart, eyes that have no light to gather, and yet are still present, still formed, as if the body has not fully accepted that sight is unnecessary here. It drifts. It breathes in the way that fish breathe, extracting oxygen from water that carries so little of it. It has lived its whole life here, and its parents lived their whole lives here. And their parents before them, going back through generations that stretch and further into the past than our species has existed. It does not notice you. You are here, and it is here, and there is 11 kilometers of water above you. Both, and the stars are up there, and the ships, and the cities, and the arguments about cobalt, and the debates in committee rooms and the satellites, photographing the surface and all the noise and urgency of human civilization. And down here, none of that exists. Down here, there is only the cold and the dark and the pressure and the sediment and the pale fish drifting, and it is enough. Whatever the fish requires of the universe, this is it. This cold, this dark, this floor, these amphipods beneath the sediment that it will find when it is hungry. The slight current, the long slow rain of marine snow drifting down from a surface world it has never perceived and never needed. It is complete here. Not surviving, not enduring. Complete. There is something in that completeness that the surface world, for all its warmth and light and richness, rarely achieves. There is no excess here, no noise beyond the geological and the biological, no urgency beyond the quiet urgency of hunger and its satisfaction. The trench floor is the most stripped-down version of existence that our planet offers. And in that stripping down, something essential remains that the noise of the surface obscures. The snailfish drifts on. The sediment settles back into its ancient stillness. Somewhere above you, too far to hear, a whale is singing. Let yourself float here for a moment. The pressure around you is 1,000 atmospheres, and you feel none of it. The temperature is just above freezing, and you feel none of that either. You are here as pure attention, pure presence, consciousness that has made the journey down without a body. And you can stay as long as you wish. There is nothing to find here tonight, nothing left to search for. The questions are still unanswered. The trench is still unmapped. The biology is still mostly unknown. The decisions about its future are still unmade. All of that remains up there in the committee rooms and the research institutions and the engineering workshops where the next submersible is slowly taking shape. That is up there. And you are here, 11 kilometers below the surface, on the floor of the Mariana Trench, in the deepest place on Earth. And it is so very quiet. The sediment does not move. The pale fish has drifted beyond your perception now, into a darkness even your imagination cannot follow. The walls of the trench rise above you on both sides, their ancient rock holding the record of 60 million years of planetary motion. The marine snow drifts down, barely visible, each particle carrying its small cargo of organic matter from a world of light that seems from here impossibly remote. Let the darkness hold you now. Not the darkness of absence, not the darkness of fear. Darkness of the deep ocean is not like any darkness you have known on the surface. It is complete in the way that only ancient things can be complete. It is a darkness that has been here since before there were eyes to notice it, and it is entirely at pace with beings unobserved. You can rest in it. There is nothing here that will ask anything of you. The amphipods in the sediment below are asking nothing of you. The microbes processing their ancient chemistry in the cracks of the subducting rock, asking nothing of you. The xenophyrophores on the trench walls, their single enormous cells going about their incomprehensible cellular business, are asking nothing of you. The snailfish, wherever it has drifted in the dark, is asking nothing of you. The trench asks nothing of you tonight, only this. Only that you were here in your imagination in the quiet of this night, and that you let the idea of it, vast and ancient and dark and living idea of it, settle into you the way the sediment settles to the floor, layer by layer, slowly, without rushing. The questions will be there, in the morning. The debates will be there. The unresolved problems of how to protect a place we barely understand from pressure we barely control will be there. Next, submersible will be taking shape in its workshop, and the next expedition will be in its planning phase, and the next set of sediment cores will be on their way to a laboratory somewhere. All of that will be there. But right now, in this moment, there is only the trench, 11 kilometers below the surface of the Pacific Ocean. 60 million years old, full of life we have not named, making sounds we cannot explain, holding in its sediment the chemical record of an ocean history that stretches back further than imagination can easily reach. The snailfish drifts in the dark. The marine snowfall falls. The walls of the trench hold their ancient silence, and somewhere in the sediment, a single-celled organism the size of a softball goes about its life with a completeness and a patience that makes everything else seem, for just this moment, beautifully small. Let the darkness hold you now. There is nothing left to find tonight, only stillness, only the long, slow, ancient quiet of the deepest place on earth, pressing gently around you like water, like the softest pressure, like the feeling of being held by something vast and old and entirely indifferent to anything but the long continuance of things. Trench does not need you to understand it. It only needs you to know it is there. 60 million years of dark, and somewhere in that dark, something pale and patient, drifting, always drifting,